First of all, thank you everyone for being here and to attending to this brown bag session. I have the honor to introduce Dr. Daniel McCafrey. He's an Associate Vice President of Psychometric Analysis and Research at ETS, where he has worked for the last decade contributing to educational measurement and evaluation and the evaluation field. He has a PhD in statistics from North Carolina State University, and previous to ETS, he worked as a senior researcher at the Research and Development think tank RAND Corporation for over 20 years. So it's with great pleasure that I introduce Daniel McCafrey to present, and without further ado, I'll pass the word to you.
Great. Thank Montserrat. I was really happy when Sergio suggested I would do this. I thought it would be fun to do this, and I'm really glad I got the opportunity. I'm going to switch over and share my screen, and you guys all know the drill. As soon as I share my screen, I can't see you. I can't see the chat. So, but I like interaction a lot more than just me talking at you. So definitely feel free if you have a question, you can put in the chat. Montserrat, I'm giving her full permission to interrupt me, but I'm also giving all of you full permission to interrupt me. So if something's confusing or you want to debate an issue or just ask something, please feel free to ask a question. It'll be a lot more fun if it's a bit more interactive. So don't feel that you shouldn't interact. And I will try not to go too long so we have a nice a couple minutes for discussion at the end, because I think that'll be fun as well. All right, let's see. Screen. Oh, good. And I'm where I want to be. All right. And you guys, okay, good. Participants could see my screen and that thing got shrunk. All right. So I'm going to talk a little bit about causal inference, and in particular focusing on instances where the data I'm using isn't necessarily a random sample from the population. And in fact, I'm going to focus most of the talk and possibly all the talk really on instances where you're working with a probability sample, like trying to make some causal inferences from a national probability sample, like high school and beyond, or the national, I forget what the drug abuse sample is, that they changed the name to that one, or one of those large samples that some of you might be familiar with, or even trying to use like PISA data or something like that, and really trying to get more towards a causal inference than just an observational kind of inference. Okay, this is work that was supported by a NIDA grant that I had with some colleagues from Rand and Temple University, and the people here are some of the people I've been working with. Beth Ann and Michael are both at Rand. Donna was at Temple and she is now at the University of South Carolina, and Yasna is a student at Temple who is trying to finish up her research. So, like I said, we're going to talk about causal inference, and I want to, before I get into the details of the specific things that's kind of novel in what I'm doing here, I want to just give a little background about causal inference. I know it's something taught a lot more commonly these days. Come on, go away. Than in the past, but still, I think I want to make sure everyone's got at least a little background in it. And so one of the things I think is really important about causal inference is we want to learn how a treatment affects an outcome. So we're really talking about we're talking about an effect. If I give someone this treatment, this will be their outcome. Not like, oh, this treatment is associated with it. People who get this treatment tend to look more like this. It really is, you're trying to sort of say, if I do X, I will see Y. So that in the future, I might see people, give them this treatment. If we have students who aren't reading very well, we know that giving them this reading intervention will improve their scores, or we can expect to see it. This is a field that's been looked at forever, and there's all kinds of issues about it. It really kind of took a major change in how it was dealt with about 40 years ago, when Rosenbaum and Rubin released a paper on potential outcomes framework and applying something that had been developed previously by Jerzy Neyman for experiments to more observational data. And this is really important because it really sets out what is truly the causal model, which is a theoretical model for the relationships that you will see among your data that then allows you to define estimands in a very rigorous way, rather than just saying, well, I've got a regression and I'm seeing things in this way or not. So it's a whole different way of sort of defining what a cause and effect relationship looks like in a way that you can then specify how to estimate that. And we'll give a little bit more details on that. So that's what people, that's a common approach that people use, is they define what they want to use using that framework. But then the question is, well, how do I then estimate that estimand? Kind of two major schools in which we do that. You can run an experiment. Experiments are great, they are the gold standard. But one of the problems with experiments, there's lots of things you really can't do experimentally. It might be unethical. You can't deny kids getting a treatment. You can't force people to be poor. You can't force people to go hungry. So, certain things you can't really do in an experiment, and other things just are hard to do in an experiment. They require sort of things on the scale or kinds of things you need to do. You just can't really manipulate in a very effective way. So experiments are limited. So a lot of what we want to learn about causation, we use observational data. Basically observational data is you're looking at data from some sample of the population where some people have treatment and some don't, and you want to use that data. And when you get there, then basically what people are going to do, they're going to make some, well, I'll talk a little bit more about ignorability assumptions. Basically, the treatment was assigned and conditional on some covariates. You can act as if treatment was assigned randomly, and then you can use regression or propensity score weighting or matching or some other method to get there. And there's a few other things people do, but in the grand scheme of things, those are kind of the two big classes of things people do. And it's a pretty elaborate set of things how you do this in both those spaces. So just give a bit more detail on what we're looking at. So we're thinking about observational data. So we're going to say we have a sample of n observations, say n people, with our treated and untreated individuals. And we're going to say that a treatment indicator, A, indicates those people who got the treatment, and 0 indicates the people who didn't get the treatment. So we'll say A is treatment, 0 is control. Then there's the observed outcome, which is the outcome of interest. So we're going to call that y-obs. So that's what you see. Have a sample, bunch of kids. Some of them got this reading intervention, some of them didn't. We didn't control who did and who didn't, but what I do then see is when they're 5th graders, I see which kids, I have a test score on how well those kids did. This might be ECLSK kind of thing, as a longer follow-up. And then we have, the other data we have is a bunch of observed covariates. And those, we're going to assume for now, those covariates were all measured before the treatment. So we don't have any issues about, well, when were they measured? Were they after the treatment? Are they somehow on the causal pathway? We're going to say we have a nice bunch of covariates that were measured before the treatment. As I said, treatment was not assigned experimentally. And the big concern with all this kind of observational data to get to our causal effects is that the people receiving treatment might be different from people in the control group in ways related to their outcomes. And this is the classic why we say, correlation is not causation, because there might be other confounding factors in there that are also going along between the people of treatment and control. So we don't know if it was the cause or those. So for treatment, we have each person in the population has 2 potential outcomes. This was the revolution that it really, I think, changed how people approach causal modeling, and was this notion that for each and every person in the population, there is a treatment outcome and there is a control outcome. Then what you do is you randomly are going to see one of those. You're not randomly going to create one of those. You're randomly going to see one of those. Each of those exists in the counterfactual universe, but you're only going to see one. And then if that's true, then for each person, there is a true treatment effect that can be defined by these 2 outcomes, y1 minus y0. How much on my test score improves if I were in treatment rather than control. This exists for everybody. The problem is I don't see it for everybody, but I can still define a treatment effect using it, and I can define an average treatment effect. What's really strong here is there's nothing in this line here that says the treatment effect for everyone is the same. They're sort of saying it can be different for everyone in the population, and this is the average. So this is it. But what's really critical here is for this to have a lot of meaning, it needs to be defined over a well-defined population and the entire population of interest, not some subset of it, not something else. If I want to say the average treatment effect for fifth graders in the United States, I need a sample of fifth graders from the United States, not a sample that's got 80% of kids from California and 20% of kids from the rest of the country. That's not going to tell me the average effect for the United States. That's going to tell me the average effect for an 80-20 California country. So you need to come up with something from the entire population. And as I said, the fundamental challenge of causal modeling is we need estimates of counterfactual means from the population, but we're only getting them from the sample of kids who were treated or the sample of kids who were in control. And it's not true. We can't assume that the kids who were treated are a random sample from the population. So we need to make an adjustment for that. So basically, as I said, how do we do this? We're going to assume that treatment is ignorable given some covariate. So basically what this is saying is that, look, if I know X, then my treatment is not related to my potential outcomes. So the kids who wind up getting A equals 1, who let's say all the boys who get A equals 1, their Y0 and Y1, which I don't get to see both, but their Y0 and Y1 are the same as all the boys who don't get treatment. So if I can focus only on boys, then I can compare the treatment, and I can compare the Y1s of the treated kids to the Y0s of the control kids and have an unbiased estimate because the Y1s of the treated kids are the same as the Y1s of the control kids. So I can get where I need to go. The other thing I need to assume that I don't have any kids who would only be in treatment or only in control because then there'd be no one to match them to. Have to make an additional assumption. It's called the stable unit treatment value. This is kind of a bit, this gets to be a bit more picky of an assumption, but basically it's saying like, look, if I see someone gets treatment, that's their treatment, that they don't have a lot of choices. This is a tricky one because it gets tricky in schools because this also says that it's not, what the treatment I get isn't affected by other people. But we're going to make that assumption today. And then one of the key things that came out of this literature that has really been a tool that has really driven for changes in how people do things is the propensity score. And that's the probability of treatment given your covariates. And one of the reasons this is really useful is people can use it for matching. But what it does is it takes that vector covariates and turns it into a single value that you can use for what you want to do, the propensity score. And one of the things you can do is you can use it for weighting. So basically, if I get a weight for each kid, but I'm going to, an inverse probability treatment weight, or what I'm going to call the propensity score weight, I can use that weight then to come up with weighted samples that I can then show would give me an unbiased estimate. And so this is the big thing. So basically, you know, a couple key points here. One, we start with counterfactuals that everyone has. We make a ignorability assumption, which is untestable, but we're going to live. But that's our trick, right? The trick for getting what we need is to make this assumption. And then we have a propensity score that kind of takes that multi-dimensional X to a single value to allow us to do something, and we're going to use weighting. We have to estimate the propensity score, and that's going to be a big question of how we estimate that. But assuming that we have a good propensity score model and we've done a good estimation of it, we can actually get an unbiased or consistent estimate of the average treatment effect for the population. So that's what we want. But one of the things here that's really key throughout all this is that this sample we have of X's and Y observed is from the population of interest, because otherwise, no matter what we do, we can't average a bunch of people from the wrong population to get the average for the right population. That's the whole problem. So where do non-random samples come from? Like I said, a lot of them come from probability samples. They might also come from non-response or attrition. Today, I'm going to focus on probability samples. The reality is almost everything I say transfers very similarly to non-response and attrition. So we're going to now say, okay, so previously we had an X, we had an A, whether someone's treated, and their Y is their outcomes. Now we're going to add to that, we're going to add a Z, and that is whether or not they're a member of the sample. Since we're all, now everybody in the population has a Z. So if you're in the sample, your Z turns out to be 1. If you're not in the sample, your Z turns out to be 0. The problem is we only see the people whose Z is equal to 1. And we're going to assume there's some covariates and sampling weights. The covariates define the probability that someone gets in the sample, and that is given by the probability of being in the sample, this quantity, P of Z is equal to 1 given U, and the weight is the inverse of this. And this is pretty standard things for survey sampling. So now we have a situation where we want to use propensity scores to deal with the non-random assignment of people to treated, but we have a non-random sample because of our non-random sampling. So now the question is, can we use this non-random sample from the population to estimate the average treatment effect for the whole population using inverse probability of treatment weighting or propensity score weighting? And how are we going to use the sampling weights when we do that? Should we use those sampling weights when we're back here? Should we use the sampling weights in here? And should we use the sampling weights when we're trying to estimate this? Because we don't know this, we have to estimate it. So the real questions that have bothered everyone were, you know, should we use it here? Most people were kind of agreeing, I bet we should use it in the estimating this stage, but there was a lot of debate about whether or not you should use it when estimating this stage, and some real debate about that. And various authors have kind of looked at this in the literature and have come to somewhat disagreements. You know, they all agree that you can get what we want using sampling weights, but they don't all agree exactly how to do it. Zanudo sort of said you don't need to use them when estimating the propensity scores. DeGraff et al. say you should use them, but they say using them when estimating the propensity scores. Dong says they're only needed in the outcomes. Austin and Lennis find no method is really preferable. Ridgway and all say weight should be used in both the estimation of the propensity score and the outcomes analysis. Most of these studies rely on simulation. And a lot of the point of this talk is questioning about, you know, can you use simulation to answer these questions? And what happens if you use simulation to answer these questions? What's interesting is that Ridgway et al., they went a step further. They didn't just use simulation. They did check with simulation, but they also derived some results to sort of show what they thought was the right answer. So what I want to do now for the rest of the time here is talk a little bit about how we can derive some results analytically. And then we're also going to see what simulations tell us, and sort of kind of get an understanding of whether simulations are really going to tell us everything we need to know, and in what ways are simulations good for checking these kinds of things, and in what ways might we want to be careful when we use simulations. So what I want to show is that, sorry, my title's wrong. This one should just be demonstration. All right, but anyway, what I want to show is, I want to show that using weights can give me something that's unbiased. Come on, I don't want to see you. And so to be able to do that, what I need to show is that the expected value of the weight times the observed value among the people who we observe in treatment and in the sample is proportional to the expected value of Y1 for the entire population. And the proportionality constant, the reason we can deal with the proportionality constant is that we've got a denominator in our weights, and that will cancel out the proportionality constant. So we don't really need to worry a whole lot about this. So basically, the weights we're going to consider using are the probability that A is equal 1 given X, and the probability Z is equal 1 given A and X. And I want to point out something here. This probability A is equal 1 given X, this is a population quantity. This isn't a sample quantity. If it was a sample quantity, it would be conditional on z is equal to 1. So the weight I'm assuming to use in my derivations is a population quantity. So I want to keep that in mind, because if I need to estimate this, I need to estimate in a way that's consistent for the population. And so if I want to estimate in a way that's consistent for the population, I'm going to need to use those sampling weights when I estimate this probability. So if it turns out I need to use this weight to get what I want, then I'm going to need to use sampling weights in this stage when I'm doing the estimating the propensity scores, and in this stage when I'm estimating, when I'm doing those weighted averages. So here's some ugly integrals, just because, you know, can't give you a talk without some ugly integrals in it. But what I want to do is I just want to walk through a little bit about the way this game is played, because basically you're going to start with a sample, and I got to get this. I want to get to the point where I have this. So I've got my conditional distribution of y and x. I'm looking at expected value, so I'm going to be integrating. I want to integrate over y. I've got my observed y distribution, and I've got x and y. So x is here. Now when I can switch x over here, given standard things we can do with distributions, and I switch x over here. And the reason switching x over here is useful is once I switch x over there, then I can start to get this thing out of here, because, right, the conditional distribution function says if a and z are independent of y given x, then conditional on x, I don't need these guys in the conditioning model anymore. So by pulling x over here, I can take z out. But when I pull x over here, I then need to work out what this guy looks like. So now I can use Bayes' theorem to work out what that looks like, and that's going to allow me to cancel this out, because this is my sampling weight. So then I can get rid of this through the sampling weight. So now what I've done is I can get rid of z in here, and I can get rid of this in my calculation using the sampling weight. And so what I now have is I can do that. But one of the things I said earlier is one of the things you want to notice here, this is in blue because this is the thing that's in question. That's a population quantity, not a sample quantity. So because it's a population quantity, I'm going to need to estimate that using the sampling weights. So as I said, if I want to do this, I need to be able to show that conditional on this, I can get this distribution, and I need the ignorability assumptions to do this. One of the things that's important here is I need an additional ignorability assumption. I can say, as you see, this is conditioning on A and Z, and I need to condition on both. So I need to come up with an additional ignorability assumption. So one of the things that's important, and I think this is something that was never given quite enough attention in the literature before, is that you need to think carefully about what assumptions you're making. So there's two assumptions you can make. One is we can assume that y1 is independent of z given x and a, which, given what else we know, we can assume that y1 is independent of a and z given x. And this implies what I said we needed all along, which is that f of y1 given x and a and z is just given f of 1 given x, which is what we really want. Or we can assume that y obs is independent of z given x and a is equal to 1, so that f of y obs is there. Now the second assumption is more defensible because the sampling probability is controlled by design. So by design, conditional on the x, because we're assuming that the same covariates are used for sampling and confounding, conditional on x, Z is independent. Sampling is independent of everything because sampling is purely controlled by what covariate group you're in, and then the sampler who designs everything. So then making this assumption under sampling has some clout. And given that this is an observed quantity, this is a more reasonable assumption. So we can then make those assumptions, and as I said, we can then take this out. Once I take this out, now I have this problem here where I have x given a. We can now do Bayes' rule again to get rid of this, and we wind up with what we need because this is just going to turn out to be the expected value of y1. So the trick here is, and the real key part here is, by going through this exercise, we need two things. We need an extended set of ignorability assumptions, and we needed to use the propensity score for the entire sample, for the entire population, not just for the sample. So that would suggest that using sampling weights when estimating the propensity scores, and we use the product of the sampling weight and the propensity score weight when estimating the weighted mean, can get us an unbiased estimate. We need to weight at both stages, right? So we want to weight at both stages. That's what the analytics have just told us. Great. Let's check it with a simulation study. So this is a pretty standard simulation. I generate a little bit more than 100,000 observations. I generate my x's to be normal. I picked a pretty benign y0. Just, I'm going to just make it a multiple of x. I didn't put an intercept in because that's just an extra nothing. So I just made it 0. And then I did what I think is a pretty common thing to do. I made a y1 is equal to y0. I made it y1 is equal to alpha plus y0, and y alpha is independent of them. So everybody has everybody has their own independent treatment effect, and that the average of that treatment, the mean of those treatment effects is delta. So the ATE is delta, right? Because y1 minus y0 is alpha, expected value of alpha is delta, so the ATE is delta. I then came up with, used a logistic kind of model to set up the probability of someone being in treatment, and then also used X to set up the probability that someone was selected for the sample. So I have a big sample, and the G is a step function, and the reason I did that was it gave me a little bit more control so that I could really work out things a bit more analytically and have some more control. But basically, it's a pretty benign simulation setup. And then what I did was, using the data I simulated, I then estimated the probability of being treatment, and using logistic regression with the sampling weights. And I only did one sample. So I didn't do like a full Monte Carlo sample because I have a really big sample. So if it's really big, and then I can probably get a pretty good sense of what's going to go on with one really big sample. It's not perfect, but it gives me a pretty good sense of what's going on. And I didn't want to do a big giant sample. I just wanted to kind of get a sense here. And I did test some of these things multiple times. So we do this. So if I do an estimate the ATE completely unweighted, I get an estimate of 1.34. The truth is 1, so clearly I get a bias. So I need to do some weighting. If I do weight both, so I weight when I estimate my propensity score, and I use the product of the weights when estimating my weighted means, just like the theory told me, I'm getting something that looks unbiased. So this is great, right? This is really good. We have some theory. I ran a simulation. My simulation tells me the same thing. I'm feeling pretty good. I could have used simulation to do this. Those ugly integrals could be ignored. I'm in good shape. Great. But I'm a kind of annoying person and like to pester myself. And so I thought, well, let's try an alternative weighting method. So what I'm going to do is instead of estimating propensity scores with the weights, everyone says, there was all this debate whether you should or shouldn't do that. I'm actually going to try not doing that. So I go back and I estimate my propensity scores, and I don't use weights this time. And I rerun everything now with my weights being the product of those, of the sampling weight, just as before. Sorry, that should, yeah, that's right, WZ. And then with the my new propensity scores, which are estimated using just the sample without weighting. So they're kind of like the probability of treatment given Z is equal to 1. All right, so my theory would suggest to me this should not work, right? Because the theory showed I should use both. I probably keyed you into, I didn't confirm the theory here. So now all of a sudden my simulation is kind of contradicting my analytic results. So this, to be honest, the way I got into this, we were working on a paper, we were looking at weighting in continuous treatments, and we had some theory, just like I did here. And then we ran a simulation, and all the simulation contradicted the theory. And I'm like, why? Why is it contradicting it? So I wanted to see, okay, if I go back to the simpler situation, can I do the same thing? And yes, I did. So then I said, well, what's going on here? One of the things that you have here is I have f of x given z and 1. I can make that f of a is equal to 1 given x and z times f of z and x. And then I can pull this out of f of x, z given x is equal to 1 times f of x. And one of the reasons I can do this is because I have the same x. The same covariates are used for sampling as they are for the confounders. I'm assuming they're exactly the same set of covariates. So then I can just use that same x. So if I would have done things this way than the way I did when I did my integration, I could have used the same setup and showed that I could use weights estimated just on the sample, not on the whole population. So it looks like maybe the mistake I made here in making this too simple was, you know, I used the same x everywhere. I used the same x for treatment assignment as I did for confounders. So maybe I oversimplified my simulation by doing that. So what if we considered the case where x didn't equal u? So now we need some ignorability assumptions, right? Because this whole world works on ignorability assumptions. So what if I have these two ignorability assumptions? First, this is the classic causal modeling one. The treatment is independent of x given some confounders, and I know those confounders. I can get a pseudo experiment by conditioning on x. And this is your classic, pretty much your classic assumption out of you know, survey sampling. Once I condition on the strata, the sampling design, then and it's true. You know, if my sample works, you know, within that strata, it's a random sample. So it truly is a random sample from that strata population or given those used. So these seem like pretty reasonable assumptions. And then they apply some other assumptions here that I might need to use when I'm going to do some of the calculations. I think a key thing to remember is you might not always be known. We might not actually know the values we use. Lots of times, like if you're using ECLSK, you don't necessarily have all the stratification variables. You don't have, because like things like districts and states are used in school sampling. And you don't necessarily have the geo information. And so we can't always assume that they're common. It may also be that things are used in the sampling that really don't have to worry about confounders. And then there's things in this actual data you get from the surveys that really are important confounders, and you only know those for some of the samples. So you can't really assume that they're the same thing. So I think this is a better case. So anyway, we can go through kind of same game. I'm going to come here. I'm going to pull my U over alone. So I need this. Now I need an ignorability assumption here that involves U and X and Y. And so the second ignorability assumption I had here is it's the trigger. This is why, you know, this is the ticket. This is why I needed that assumption. We can go through a lot of the same exercises. I'll share the slides. If you're as obsessive about, you know, going through this kind of algebra as I am, you can do it on your own, but basically it's the same game I played the last time. Lots of details, but eventually I get down to this. I have FOBs with X and Y, which is what I wanted. But again, now when I'm going to pull this out, right here it is again. There it is. There's that propensity score on the entire sample. And now I don't have the same X and U, so I couldn't use that same game I did last time. So now I'm showing the same thing I showed last time, right? To obtain unbiased estimates, we can weight at both stages. Weight by the product of the sampling weight and propensity score when getting that weighted mean, and weight by the sampling weight when estimating propensity score. Same conclusion as last time. Same simulation as last time, except now I generated some U's. The same idea. The U's are related to the X's. A real key thing here is my model for Y doesn't involve U, and my model for the treatment, my propensity score, doesn't involve U. Go through the simulation study. I'm going to estimate my logistic regression using my sampling weights, and I'm going to have my sampling weights based on those, and I'm going to get my weighted estimates using the product of the weights, just like I did last time. Key thing, I'm going to be using those sampling weights because that is what all this nastiness just told me to do. All right. So now this is great. Big bias if I don't weight, no bias if I do weighting at both. I did the alternative again. And yet again, simulation contradicting my analytic results. But in this time I don't have U and X, same U, same X. So that wasn't the thing that was going on. Well, this is a little more subtle because there are alternative ignorability assumptions. Like I can make a bigger, bolder ignorability assumption. I can assume that Z and U are also independent of A given X. And then I can assume that my observed values are independent of Z given U. Okay, well that one's fine. That's kind of just one we've had. Oh no, I can assume these aren't the observed values. These are the counterfactuals are independent of Z given U. Well, maybe that even makes sense because basically everything is independent of Z given U. So this wasn't much to make. And this one, I don't know. Maybe it's a reasonable one to make. But it's somewhat hard to justify. However, it holds for the simulated data. And under this assumption, under this ignorability assumption, I can go through my painful sets of integrals and I can come up with this as my propensity score and still get consistent estimation, still get an unbiased estimate, still show what I need to show. So what's going on here is that when I did my simulation, I baked into my simulation an ignorability assumption I hadn't really given much thought to. I was giving it the ignorability assumptions I thought I wanted, but I had baked in a lot stronger ignorability assumption. So remember what I did was I had baked in that U and X weren't included in these models. And so that allowed me then to wind up not needing to use the sampling weights in both stages. So the question is, do I really need to use the sampling weights in both stages? Is this maybe not that meaningful? You know, maybe the analytics are kind of not right. Well, I'm just going to skip that. One of the other things I can show is that if I don't use sampling weights, I can actually get this. It also works with sampling weights only for estimating the propensity scores. So what's going on here? Like, why are all these things working? Well, there's more alternative ignorability assumptions that we can consider here. And one of the things that's going on here with these other ignorability assumptions is I also baked something else into my estimates, that if expected value of y0 given z is equal to 1 minus the expected value of y0 is equal to the same thing for y1, then I don't need to use sampling weights at all. And this is going to hold whenever the individual treatment effects are not functions of the covariate. So let's go back here real quickly. Let's look at my treatment effects. My treatment effects are alpha. They don't depend on covariates. So basically, I don't have any interactions in my model. And because I don't have any interaction in my models, I don't need to use sampling weights at all. And so again, whether I thought about it or not, I had baked into my sample a case where I didn't need to use the sampling weights. And as you can see, because like y0 is this, oh, I'm sorry, the line got missed there. So the expected value of y0 given z is equal to 1 is the expected value of x given is 0.75 times the expected value of x is equals 1. So that's what will give me a biased estimate of y0, the expected value of y0, but the expected value of y1 given this, and that should be delta, is delta plus the expected value of y0 given z is equal to 1, which is delta plus 1 times 0.75, so the expected value of x given z is equal to 1. This is the same quantity as shows up here, so their difference winds up not to matter, so I don't need to use sampling weights. So I modified my simulation one more time so that it no longer meets those independent ignorability assumptions, and by adding in an interaction basically, and not making it meet any of those other alternative ignorability assumptions. And now when I do it, nope, I don't think I really want to do that right now. Unweighted, and the real answer is about 3.12. So if I do it unweighted, I get a big bias. If I do it with both, I get something that's right. If I do it with weighting the outcome only, not weighting when I estimate the propensity score, I get something that's close, but it's not right. And this actually is biased. The bias is small, but given how large the sample is, that truly is biased. So there is a small bias that's going to come up weighting only the outcomes, not weighting the propensity scores. And if I weight neither, now I also have a big bias. So what I've shown now, a lot of details here, but I want to go over, I'm going to skip that, I'm going to skip that. What I want to go to is, I think, the key points here. So what did I do? So I showed that I can derive analytically a result. It sort of says, if I use the weights in both stages, I can get an estimate. But I want to point out something about that statement. It didn't say I must use the weights in both stages. And as I showed, there are conditions in which I don't need to use the weights in both stages. The reality is in almost, and I looked at this many ways, in almost every case, and I think in every case it is all reasonable to be a good set of assumptions, using weights in both stages will give me consistent estimates, will give me unbiased estimates. But I don't necessarily have to use weights in both stages. And so the reality is both the simulations and the analytics are right, because neither one is really getting to all the subtlety if you just do the first thing. If you just look at the analytics, you forget that you found a sufficient condition, but not a necessary condition, right? If I do this, I get what I want. That doesn't say if and only if I do this, do I get what I want. And if it's going to be necessary, I need the only if. The other thing I showed was like, oh, what looks like just a very benign, very obvious, just the right thing to simulate had baked into it a lot of assumptions that I didn't really see when I first looked at it. And these sort of simple cases had told me something that wasn't true. And, you always say, yeah, the classic thing with simulations, your final caveat is the simulation results are limited because it's only one set of simulations. And we all kind of roll our eyes and take that for granted. But I think this really showed you in a very subtle way that the simulation was limited. And what the limitation meant was that you we're missing things and potentially giving the wrong answer. So the reality is, I think what this really demonstrates is if I want to do this, I can buy insurance, and almost anything I do, if I wait at both stages, it's really unlikely I'm going to get a situation where that's going to give me trouble. So if I do wait at both stages, I probably am in a very, very good condition where I will get an unbiased estimate. So waiting at both, assuming that my models are correct and all other things, let's not bring in some other problems. So if I wait at both stages, that's good, but it doesn't have to be. And waiting at both stages doesn't come for free, because this is statistics. And in statistics, the world is you never get free lunch. There's always a bias variance trade-off. There's always a trade-off. So I can assure myself I don't get biased by waiting at both stages, but then I'm going to probably have noisier weights, so I could wind up in loss of precision. So maybe I don't always want to do that. So, maybe I need to do some empirical checks, because if I don't have any interactions, if it really doesn't look like, what I know about the sampling design is influencing my treatment outcomes or influencing my probability of being in treatment, maybe some of those simpler assumptions, some of those other kinds of ignorability assumptions really work, or that I know my model is simple and a kind of simple model will work. So I think that's the real important thing. I also think that we really need to be very careful when we're saying we're going to use simulations to test something, because it's really hard unless you really know the situation very well, so you can really make sure that doesn't cover all situations, is not missing obvious ones that where you're baking into your simulation the results without really knowing that you're doing it. So I'm going to stop there and give us about 10 minutes for questions. And yeah, so maybe I want to stop sharing my screen and I can go back to it if need be, so I can see people. No, I don't want new share. That wasn't what I wanted. I want to stop share. Great.
Thank you so much for your presentation. It was really interesting.
Good.
Does anyone have questions? You can raise your hand and we can start the session. I do have one question.
Yep.
It's really interesting because I don't know how everyone else gets their education in measurement and evaluation, but a lot of what I've learned was, building theory through simulations. So with this example, I wonder if you can give us a more, I don't know, in my mind, of course, I think of international large scale assessments because that's my area, but can you tell us, for example, if PISA or something like this would actually work, given that they already have a very complex design when it comes to sampling?
Yeah. So I think there's two things that I'll gonna respond to one thing you said before you asked your question, then I'll respond to your question. So the first thing you said was we kind of learned things through simulation, like learn theory through simulation, and I think that's a really good thing to do. And I think one of the reasons that works well is lots of times the basic theories you're learning, you can get a lot of the intuition from simulation. And I would never argue not to do that, because I would know nothing if I didn't do that. But you do have to be careful not to mislead yourself. And one of the reasons it works well when you're learning those things is that people do understand the situations pretty thoroughly. So the simulations they kind of suggest you're doing, especially in classes, they kind of know they're not giving you sort of misleaders in the simulation design. So it kind of helps in that space. But you do always have to be careful, even in those cases, not to sort of give yourself bad intuition by oversimplifying your simulations, which is a message I need to give to myself, because I do, like I said, I do a lot of that to sort of do things, to check things. And a lot of times also you kind of have a bit of a theoretical result and you simulate them to kind of check things. So you're really kind of doing a bit what I was doing in the last simulation study, which is, okay, I've kind of laid out through some theory what needs to check. So now it's a question, if I simulate, given what I just showed should be a problem, will it be a problem? Then I can show it was a problem. The question is about things like like PISA, and I think that's a great question, because PISA is exactly the kind of test case, right? It's non-random samples in every country. Lots of people use PISA to study what they may not claim it's causal, but their interpretations sure sound pretty causal. And they use a lot
Yes.
of covariates and things to kind of make adjustments to get there. I
Mhm.
think that whether or not it's really gone, whether or not how you would need to do weighting in those cases probably depends a lot, somewhat on the specific questions you're asking. The designs are pretty complicated in various countries, and it's a little tricky there, because in different countries the designs use different factors, so they don't use the same sets of covariates in every country. So you may be very interested in using um, the same covariates to deal with confounding in each country, but they may be using very different sampling uh, uh, variables to design their samples, because they have different issues. So like, in some countries there are really big urban rural differences, so they oversample rural places. In other countries, that's not something. Some countries have language groups or ethnic groups that they oversample for. Other countries don't do that in similar ways. Or every country may oversample for ethnic groups, but every different country has different ethnic groups, so you
Mhm.
can't use that as a common set of things. So as I'm thinking, without much thought, it would seem to me that peace is probably a good example of a place where taking the buy some insurance by weighting in both stages would be, if you were doing propensity scores, might be a good idea, because of the fact you've got these differing kind of issues with the sampling. Um, and because it's a real sample rather than an idealized sample, not everyone who sampled does respond. So even some of the sort of classic um, sampling assumptions are a bit more tenuous. So it seems to me like that would be a case to look. Although you could look to do some looking and see whether there really are some interactions. Well, the other thing is, because you don't even know what all the sampling variables are, in one country the sampling variables might have an interaction with the outcome. In other ones they don't, because they're just different. So it does feel like a case where maybe that would be a good example where using sampling weights in both stages would be helpful, because you don't have to worry about whether any of these other kind of things are holding that would make it be a problem.
Right, right. That makes sense. Well, thank
Yeah.
you so much for your
Yeah, and that's
answer.
a good question. Nice to think
Anyone
through.
else has a question? You can also type it in the chat if you want, or unmute yourself. I think it was really interesting. So thank you so much, Dr.
Sure.
McCafrey, for your presentation. Um, I
Yeah.
wonder if it's interesting, right? Because as as everything, there's not a white or black answer that says use this
No.
method and do it this way only
Yeah,
across
I know.
all
I
the
think that
studies.
I think that's it, and I think that's. I'm glad you brought it up, because I think that's another sort of sub theme of this thinking, is that one of the things I think going into this, and in the literature, you definitely get this feeling on these kinds of questions that people wanted to come up with. This is what you have to do, and that, you either do or you don't wait in the first stage, and that's kind of universally what you should do. And this is a recommendation, and you know, and and I, papers were really working in that space. But that, I think, in what's the reality is, and what this talk kind of shows, is that's really rarely the case. That in almost all the applied work we do, one of the reasons applied statistics, applied psychometrics
Mm.
is something we can all continue to work on forever and get better at forever, is because there isn't, in most situations, which once you get beyond kind of simple situations, there isn't one right answer. There isn't one obvious thing that so clearly is the only way you would do things that you can do it. Yes, if you've got a likelihood, maybe it makes a lot of sense to maximize the likelihood, but there's a lot of situations about, well, how do you set up that likelihood? What are the kinds of situations? What are the assumptions you need to make? How good that is? How do you test? It's not that simple. Like, the world isn't just that one likelihood model. Or you know, as we're getting into more complex latent variable models, lots of different ways you can turn, places you can go, things you can put in models or you can't. And it's not clear which ones are right because you just don't know the right thing. So I think there are, you know, it is the reality that there isn't a clear answer. And this kind of shows one of the reasons why there isn't, because there are very different assumptions that we kind of take for granted. Oh, here's two assumptions I made. They seem to be it. They work and I'm good. But the reality is there are even lots of alternative ignorability assumptions you can get into here. And they all kind of give you, sometimes they can give you different things. Lots of them give you the same thing, but they don't all do that. So there's lots of alternatives you can consider.
Yeah.
Yeah. How many do most of you learn some sort of causal modeling now? Is that a real common thing for you guys to have in your coursework? Some nods, yeah.
In my case, it was mostly experimental design. So,
Okay, yeah.
So as
Yeah,
you
that
said,
would
the
make
gold
sense.
standard. Sergio,
Yeah,
please go
yeah.
ahead.
Oh, what happened to Sergio? Yeah.
Hi. Yeah, thank you for the presentation.
Yeah.
Unfortunately, I couldn't join from the beginning, so hopefully my question is not stupid
Oh, no.
because of the part I missed. But yeah, I mean, I think what I appreciate a lot of what you presented is this idea of not not accepting right away like what is sufficient, but also thinking about what is necessary, trying to kind of like push and also to kind of like go a little bit further on the assumptions that are behind whatever you are doing.
Yeah,
And
yeah.
so I wonder because I think when you start to think in that way, then it's that you start to realize much more details and much more complexity that maybe you didn't see at the beginning. So I wonder from where that motivation came, like why you said that you wanted to be like more and you wanted to look for these like necessary conditions also, but like why you it was like an intuition that could be that could lead you to something better. Like I'm curious about like your
Yeah,
thinking
yeah,
of
yeah.
why to try.
Right. Why, like, why sit here and sort of like, hey, you got a good result. Why break it? The reason was, and I mentioned this, I think, before you did get on the talk, but I think it's good to reiterate this is that we were working on this paper, kind of trying to extend the results from this dichotomous case to a continuous treatment case. So like you might have something like exposure to like doses. So, you know, you might say how many, like time that a kid was in a classroom. You might sort of say, you know, rather than did they get a treatment, you know, how long were they in a classroom getting a treatment? So treating that as like a continuous exposure. And when we extended the weights, I derived some results that showed these similar kinds of sufficient results, and sort of said, okay, looks like you should weight at both things. And we ran a simulation, and the simulation results pretty much said, no, you don't need to use the weights. In fact, sometimes you don't need to use the weights at all. I'm like, why is that? And I really had a hard time breaking it. It's like, you know, what do we do? So I was really trying to figure out like why doesn't do. So I didn't want to work in the continuous space because that's just messy and hard. So I started fooling around in the dichotomous space to understand why we were getting these inconsistent results. And that's when I kind of started to break down like, oh, I think the first thing I figured out was the last thing I showed was like, hey, the treatment group is the treatment group has, you know, if the treatment and control groups just differ essentially by the same bias, then it doesn't matter. And that's a fairly common thing for people to do, the kind of thing I did. Like you generate Y0 and you add in some sort of treatment effect. In fact, I went even bigger than some people do. Lots of times they add in a constant treatment effect. And so that's a really common thing for people to do. And so, so that's a common one to bake into something where that would cancel it out. The so that was really the motivation, was just trying to understand this. But yeah, I think you know, you're right. we want these necessary conditions, but I think necessary conditions are much harder to get. And I think what I really learned through this exercise is there are no necessary conditions here. That there are situations where definitely you need to use weights in both situations, but there are lots of situations where you don't. So, there isn't a situations where this has to be what you do, even in this kind of very somewhat circumscribed situation, as opposed to like, how do you run a regression, like what's the right model. But this is kind of like, even if I assume everything, I know everything, there isn't like, you just can't know, because it really depends on the conditions of your data and your application, whether there makes sense that there's a nonlinearity, or whether that no interaction kind of works and makes sense for you. The other thing we found is that in the continuous case, like even just assuming normality for certain things added in another way to get rid of a certain kind of bias. So like that one's even more tricky. And so like, oh, normal's benign. We always use normal. It's nice. It's easy. It works. It's like, ooh, well, assuming normal kind of added one more space where it made something simpler, that if it wasn't normal, then there could introduce bias, but normality sort of masked the fact that that bias could be there. So yeah, it's an interesting case. It's like and I actually was able to write down some situations where, under certain weird ignorability assumptions, weighting in both stages could cause bias, but not weighting in both stages wouldn't. But those ignorability assumptions just don't seem like ones that would. And I'm not even sure you could create them in reality. Like I couldn't think of a way to simulate data according to them. So I'm like, I don't know about these, but but in theory I could write them down. So yeah, so I think the reality is lots of times necessary conditions would be what we all want, but the reality is they often don't exist. And especially in this whole causal modeling space. J.R. Lockwood and I were doing work at one time. We kept trying to come up with necessary conditions, and I think he found some necessary conditions, but even those, we did find necessary conditions, but even those were kind of somewhat special, how they had to be necessary conditions.
Thank you so much.
Yeah. Well, thanks a lot for the opportunity. This was fun. Hopefully you guys found it useful, and yeah, good luck with everyone. I'm sure some of you, if you're still taking classes, this is probably not the easiest of week to give up an hour for a talk. So thanks a lot for joining me.
Thank you so much again.
Right.
Thank you for joining us. We have a lot of exciting activities in the GSIC coming up. 2 more writing circles at 11 a.m. today and next Friday. And on January, we have the socials, the writing circles, and a lot of other activities coming up. So keep connected. Have a great finals week. And thank you again, Dr. McCafrey.
Yeah, so long. Everyone have a good weekend. Bye.
Bye-bye.